Welcome to Oslo, and welcome to the Norwegian Academy of Science and Letters. For over 100 years, this beautiful building has welcomed the finest minds of Norway and beyond. But we're here today for a very special reason. We're here to discover who has won the 2026 Abel Prize for Mathematics. So come with me behind this door.
As the president of the Norwegian Academy of Science and Letters, it is my pleasure and privilege to announce the winner of the Abel Prize for 2026. Our board has decided to award the Abel Prize to Gerd Faltings for introducing powerful tools in arithmetic geometry and resolving long-standing Diophantine conjectures of Model and Lang.
Dear Professor Gerd Faltings, on behalf of the Norwegian government, I would like to congratulate you as the Abel Prize laureates for 2026. Your great achievements in arithmetic geometry, solving mathematical puzzles like the Model and Lang conjectures, make you a highly worthy recipient of this prize. The world depends on science to handle our many common challenges. By honoring exceptional mathematicians like yourself, who have made significant contributions to basic research, we hope to inspire further innovation and collaboration, motivate new generations of mathematicians, and strengthen public appreciation of scientific achievements. The Abel Prize is a celebration of you as an outstanding mathematician and of the field of mathematics. Congratulations as this year's Abel Prize laureates. I am looking forward to welcoming you in Oslo and Norway in May.
Gerd Faltings receives the 2026 Abel Prize for introducing powerful tools in arithmetic geometry and resolving long-standing Diophantine conjectures of Model and Lang. Solving polynomial equations over the rational numbers is a long-established fundamental part of mathematics. Systems of such equations, which are known as Diophantine equations, can be classified initially by the complex dimension of their solution set. The case of dimension 0 is already non-trivial and addressed by Galois theory. Dimension 1 is a case of curves, which are classified topologically by their genus. The genus of a complex curve is a number of holes in the corresponding two-dimensional real Riemann surface. The Diophantine problem for curves of genus 0 is governed by the Hasse-Minkowski theorem. A curve of genus 1 gives an elliptic curve. Henri Poincaré conjectured in 1901 that the group of rational points on an elliptic curve is finitely generated, and this was proved by Louis Mordell in 1922. In the same paper, Mordell conjectured that the curve of genus 2 or more has only finitely many rational points. This became the central open Diophantine problem for the subsequent 60 years, until it was proved by Faltings in 1983. As an example, the result of Faltings establishes the finiteness of rational points on all smooth plane curves of degree 4 or greater, including the famous Fermat curves x to the n plus y to the n equals z to the n for n greater than or equal to 4. Faltings' breakthrough proof surprised the experts. Rather than employing Diophantine approximation, his approach was via resolving an important case of a conjecture of John Tate, as well as a conjecture of Igor Shafarevich. In 1989, Paul Wojta found another proof of the Mordell conjecture, following the more traditional lines initiated by André Weil and Carl Ludwig Siegel. In 1991, Faltings adapted this approach to prove a vast generalization of the Mordell conjecture, namely the Model-Lang conjecture of subvarieties of abelian varieties. An abelian variety, generalizing an elliptic curve, is a complete projective variety having a group structure. Mordell's finite generation result was extended to rational points of abelian varieties by Weil. Here, rational may be taken to be over any fixed number field. The Model-Lang conjecture describes the distribution of rational points in any subvariety of an abelian variety. More precisely, it says that all such rational points are contained in the union of finitely many subsets of the given subvariety, each of which is a translate of an abelian subvariety by a rational point. To prove the Mordell-Lang conjecture, Faltings established a Diophantine approximation result known as Faltings' product theorem. This generalizes a key result of Klaus Roth used in the proof of his celebrated theorem on the approximation of algebraic numbers by rational numbers. In 1994, using the product theorem, Falting and Gisbert Witzholz gave a new proof of Roth's theorem and his multidimensional generalization known as the Schmidt subspace theorem. In his 1991 paper, Faltings also proved the finiteness of integral points on affine subvarieties of abelian varieties, as conjectured by Search-Lang. Faltings' work still stands as a central pillar in modern Diophantine geometry. Classical Hodge theory relates the topology of complex manifolds to the differential geometry. In a similar spirit, P-adic Hodge theory studies the natural structure carried by the cohomology of algebraic varieties over p-adic fields, where Galois and Frobenius actions encode arithmetic and geometric information, respectively. Faltings made major contributions to p-adic Hodge theory, giving proofs of the main conjectures formulated by Tate and Jean-Marc Fontaine, and extending its scope to the non-abelian setting under the name of p-adic Simpson correspondence. The conjectures of Tate and Fontaine relate p-adic et al. Cohomology, which plays the role played by Betti cohomology in the classical theory, and de Rham cohomology. The non-abelian version relates the p-adic representations of the fundamental group and Higgs bundles. Tools introduced by Faltings have proved crucial to subsequent developments in p-adic Hodge theory and commutative algebra. These include the purity theorem and its notional almost et al. Extensions, clarified through the work of Ofer Gaber and Lorenzo Romero, and subsequently strengthened by Peter Scholze. Elliptic curves over complex numbers are parameterized up to isomorphism by points on the modular curve. The modular curve arises as a quotient of the upper half-plane by the group of 2 by 2 integral matrices of determinant 1, acting by linear fractional transformations. Abelian varieties are similarly parameterized by the points of Siegel modular varieties. Faltings, in a 1990 monograph with Xing Li Chao, constructed an arithmetic compactification of these varieties. The work became a cornerstone for subsequent developments in the theory of integral models and compactifications of Shimura varieties. Gerd Faltings is a towering figure in arithmetic geometry. His ideas and results have reshaped the field, settling major long-standing conjectures, while also establishing new frameworks that have guided decades of subsequent work. His exceptional achievements unite geometric and arithmetic perspectives and exemplify the power of deep structural insight.
That was quite a mouthful, Helga.
Yeah, I'm sorry about that. This was written for the mathematical community, and in particular the expert. But at the base of this year's Abel Prize is number theory.
Yes, I heard a phrase, arithmetic geometry. Do you think you can explain what that is?
Yeah, the starting point is equations. And these equations have solutions that are integers, so numbers. But these equations can also be visualized as curves. And there you have geometry. So it really combines number theory and geometry.
And I also heard the phrase Diophantine conjectures and Diophantine equations. Can you tell us what those are?
Yeah, these equations are named after the Greek mathematician Diophantos. So let me take one example. So in the old days, where we were still paying with coins, if you were to pay for something with a precise amount of coins, say 1 kroner, you could either do it with a 1 kroner coin, or you could do it with 2 50 krones or 25 krones. And if you're out of 1 coins, you couldn't really pay 6 exactly. And these Diophantine equations are equations with integer solutions. So equations with integer solutions, or more general fractional solutions, so ratios, are called Diophantine equations.
Well, thank you, Helga. I understood that. So that's surely too basic for an Abel Prize.
Yes, let's fast forward from Diophantus to Mordell. So Mordell, who was a mathematician, conjectured in 1922 that a big class of equations could not have infinitely many solutions, but could only have finitely many solutions. And he tried to prove it, but he could not. And this claim was really the big unsolved problem in this area of mathematics for 60 years.
And then this year's Abel Prize winner takes up the challenge.
Yes, indeed. Gerd Faltings was a very young and exceptionally talented mathematician who wanted to have a look at Mordell's conjecture. And working very hard on it, eventually he could actually solve it and turn Mordell's conjecture into Faltings' theorem and prove that Mordell was right.
How was this received in the mathematical community?
This was a big hit in the mathematical community. Experts were totally surprised by this, both by the proof and also the method of the proof, because Faltings did not use a proof that was following what people expected as a proof. And this problem was considered all too difficult for mathematicians at the time. But Faltings was able to solve it. And in his proof he used abelian varieties, named after Niels Henrik Abel, who gave the name to this prize.
Well, I'm glad to hear that Abel's work is still opening doors for mathematicians working on difficult problems today. But does Faltings' theorem tell us what the solutions are to these equations?
No, first of all, he doesn't give a recipe of finding the solutions, and he cannot tell if there is a billion solutions, 5 or 0 solutions. And indeed, Andrew Wiles, when he proved Fermat's theorem, which is a special example of what is contained in Faltings' theorem, he showed that there are 0 solutions to his equation. And for mathematicians, the distinction between infinite and finite is huge. It's really infinitely big. So I should add that Faltings, in addition to his proof of the Mordell conjecture, has done many other very important results, but they require more mathematical knowledge to explain.
Well, thank you very much, Helga. Numbers. The basic stuff of mathematics. You can add them, multiply them by themselves, any number of times. You learnt the basic rules to do that at school. Number theory is one of the oldest branches of mathematics. Back in the 3rd century CE, a mathematician called Diophantus of Alexandria introduced some problems that are still giving mathematicians headaches today. Because although the rules of how numbers behave when you add them or subtract them or when you multiply or divide them seem simple, when you start to mix multiplication and addition, things get very mysterious. Diophantine equations have more than one unknown variable, represented by a, b, x, y, and so on, and solutions that can be expressed as integers, whole numbers. Pythagoras' theorem is a Diophantine equation. A squared equals b squared plus c squared. The whole number solutions for a, b, and c are called the Pythagorean triples, and there are infinitely many of them, starting with 3, 4, and 5. And if we square them, we can see that 3 squared plus 4 squared equals 5 squared. But what if instead of squaring a, b, and c, you cube them? Not so easy to solve. In fact, Fermat's last theorem says that there are no Diophantine solutions for a to the n plus b to the n equals c to the n if n is greater than 2. And sure enough, for hundreds of years, nobody was able to find any whole number solutions if n is 3 or more, if the equation has degree 3 or higher. But it took from 1637 until 1995 for Abel Prize winner Andrew Wiles to prove that there cannot be any such solutions for any n greater than 2. One way for mathematicians to understand the deeper patterns of numbers is to represent them as geometric shapes. This is the field of arithmetic geometry. Equations can be expressed as sets of points by turning the equation into a function and plotting the solutions as coordinates. So the equation x squared plus y squared minus 1 equals 0 can be expressed as fxy equals x squared plus y squared minus 1. And then we study where this function equals 0. If we plot this on a flat sheet of paper, it gives us a circle, passing through the points where x equals 1 or minus 1 and y equals 0, and the points where x equals 0 and y equals 1 or minus 1. Any point on that circle gives us values for x and y which solve the equation. But those four integer solutions, which are obvious, or trivial as mathematicians would say, they are the only whole number solutions. But we can find infinitely many rational numbers that satisfy this equation. For example, x equals 3/5 and y equals 4/5 is a solution. So if you're prepared to make the numerator and the denominator large enough, there are an infinite number of rational points on the curve. They're called rational numbers not because they behave in a sensible way, but because they can be expressed as a ratio between two whole numbers, also known as fractions. But far more of the points on this circle are irrational numbers, so called because they cannot be expressed as a ratio between two whole numbers, though they may be approximated by fractions if you make the denominator big enough. If that sounds bizarre, think of the irrational number pi. Its true value cannot be expressed as a fraction, but for practical purposes, we can approximate it as 22/7, or 3.142, which is 3,142/1000. But the closer we want to get to its true value, the greater the numerator and denominator need to become. This is Diophantine approximation. So that equation, x squared plus y squared minus 1 equals 0, has integer solutions, rational solutions, and irrational solutions. But if we change the power to 3, x cubed plus y cubed minus 1 equals 0, there are no positive rational solutions. Difficult equations involving both multiplication and addition can be expressed as curves in number fields. A field is a set of numbers with some rules for how the numbers behave when we add or multiply them or try to put them in some kind of order. The number field Q, for example, includes all the rational numbers, that's Q for quotient. The complex numbers, which include I, the square root of minus 1, form the number field C. A polynomial equation includes different powers of the same variable, like x cubed plus 3x squared minus x plus 1 equals 0. And the higher the powers, the greater the degree of the equation. And from the degree, we can determine the genus, which tells us how many holes there will be in the curve. Elliptic curves are given by cubic equations, such as y squared equals x cubed plus ax plus b. So they have degree 3. That means they belong to genus 1. And the curve, defined by f x, y, z equals 0, has one hole. Like a ring donut. Andrew Wiles used elliptic curves when he proved Fermat's last theorem. In 1922, Louis J. Mordell proved that the rational points on an elliptic curve are generated by a finite group of points that behave in predictable ways, an abelian group. But what about curves of genus 2 or more, described by equations with higher powers? Unfortunately, they don't follow such straightforward rules. Mordell conjectured that such curves only have a finite number of rational points, but he was unable to prove it. In 1983, Gerd Faltings proved Mordell's conjecture, which is now known as Faltings' theorem. It was a major achievement, especially for one so young, and the beginning of many important results in number theory. Hello, Professor Faltings. It's very exciting to meet you and congratulations on winning the Abel Prize 2026.
Thank you very much.
I wanted to ask you, what was it about mathematics that first excited you, that first made you want to study mathematics?
I think it was that there's a clear distinction between true and false. I mean, you either prove or not. Well, for example, in school in literature, there were various ways to think about it and different interpretation and so on. And I didn't like that too much.
You were very young when you proved the Mordell conjecture. I think everyone was surprised. Were you surprised?
Well, I was surprised, but well, maybe Abel was still alive in my age, but he also died, yeah. Well, he died, yeah.
Did you feel that you had some urgency, that you should get some work done really quickly?
No, I was, I mean, in the beginning of my career, I wanted to get tenure so that I could live off my work. And I got this, and then I suddenly got very lucky with the Mordell conjecture. And since then, I'm sort of traveling first class in mathematics.
What kind of impact does it have when you get such an amazing result so young? Because you were not even 30. Were you 30?
No, when I proved it, I was 83, I was 28.
People were surprised by the method you used to solve it. Did you set out to prove it, or were you looking for something else?
Well, there was a friend of my advisor, Luc Spiro, who lived in Paris, and he had ideas about Mordell. And I thought they sounded interesting, and I thought, well, I can work on it, probably I won't prove it, but I will get something interesting out of it.
But you proved it by quite an unusual method, didn't you? Can you explain briefly why people were so surprised by the method that you took?
I mean, the things which were natural maybe from Spiro's point of view, and I was sort of lucky that the people in Paris didn't quite take him serious, and so I had not so much competition. So I did things which were natural from its point of view, and I suddenly was successful.
A lot of your great work has been in number theory. To a non-mathematician, that sounds like, but isn't all mathematics numbers? Can you explain, in a way someone who hasn't done mathematics since school would understand, what is number theory and why is it so interesting for mathematicians?
Well, number theory, I mean, it starts with the integers 1, 2, 3. We usually can count so far, and then you try to do things to solve equations in these, and it's sort of an elementary thing, but you get interesting questions, and for some people like me, it's interesting. I guess for others, it's not so interesting.
But the work you're doing is much more mysterious, isn't it? Numbers behaving in mysterious ways. What were the puzzles that made you think, well, this is interesting?
Well, I mean, mathematics has been done since centuries, and naturally things evolved, and sort of things which we do in school maybe are, 300 years old or so. And naturally the theory has advanced. We are far away from the elementary things. Well, we had this old field of number theory, and it sort of has also certain romantic appeal, but there are, of course, other fields. I mean, you want to compute orbits of space vehicles and so on.
You've been at the Max Planck Institute for a very long time. What does that enable you to do? What's special about being there?
Well, being there is that you have a few obligations, and besides doing research. And so I could do this for a long time. Well, I did some teaching at the university here, because we have a good relation to the university. And also teaching is good for you, because you have to talk with ordinary people and have to learn how they think and to explain things. So teaching without keeps you down to earth.
Oh, that's interesting. What advice, if there was a young mathematician starting now, I mean, maybe looking for a PhD subject even, what would you suggest to them? What advice would you give?
I think for a young guy, well, my advice has always been not to look what might make you famous. Well, that get the Abel Prize, but to do things which you like. I mean, to choose a field which you like and find interesting and then work on this.
So finally, you say you're left with the problems you couldn't solve. So what are the problems you're still working on?
Degree of Weyl parametrization for elliptic curves. And well, I find it very interesting, but I don't get ahead. So that's my, well, as I said, you are left with the problems which you can't solve.
Is it possible to solve?
Well, I don't think it's impossible, but it gives me a pleasure to work on this.
Thank you very much, Gerd Faltings, and congratulations again on winning the Abel Prize 2026.
Thank you very much.
Thank you. This is such a well-deserved award and such a great year for mathematics. But tell me, Annalyn, why was the Abel Prize established?
The Abel Prize was established by the Norwegian Parliament in 2002 on the occasion of the 200th anniversary of Niels Henrik Abel's birth.
2002. So the mathematicians among us will realise that in 2027 we have another anniversary coming up.
Yes, exactly. Next year is the 25th anniversary of the Abel Prize, and preparations are already underway. But now we must focus on celebrating this year's winner of the Abel Prize. I would like to thank the Abel Committee for their outstanding work. It is a pleasure for me to welcome you all to the Abel Prize Award ceremony at the University Aula in Oslo on Tuesday, 26th of May at 2 p.m. Norwegian time. Gerd Faltings will receive the Abel Prize from His Royal Highness Crown Prince Haakon. There will also be a lecture in honor of the laureate at the University of Oslo on Wednesday, 27th of May. Registration will soon be available through our website, and you are most welcome to Oslo to celebrate this year's Abel laureate with us.